Good day, everyone. I am Takis Villafranca, and today me and my groupmate will be presenting our project for Data Science number 1. So, to start, we start with part A, which is the data acquisition and pre-processing of the data. So, here, the data, the specific Kaggle dataset that we chose came from the Devastator, titled Online Retail Sales and Customer Data, and we chose this data set because it provides a clear real world transactional data along with details regarding invoices, products, quantities, prices, and customer IDs. This dataset also supports both customer behavior clustering and market basket analysis, making it suitable for our goals. Its strengths lie in the availability of multiple invoices per customer, allowing frequency and monetary metrics to be calculated. However, it lacks explicit demographic details and data quality issues such as cancellations and missing data values must be handled carefully. So next, we have the data loading, which was utilized with the data frame, pandas, and the initial exploration. So to understand the dataset structure, we used firstly df head, which displays the first 10 rows of the dataset to get an initial view of the data, and because it helps in understanding the layout, column names, and spotting any immediate issues. Next, we move on to the data frame info, which provides a concise summary of the data frame, including column names, non-null counts, and data types, which is essential for checking the data integrity and identifying missing or malformed entries before analysis. And then after that, we utilize df.isnull.sum to identify missing values and inspect the data types, and we also utilized df.describe to uh, give descriptive statistics for the numerical columns such as mean, std, mean, and quartiles. It is useful for understanding the data distribution and detecting anomalies or outliers within the dataset. So as stated earlier, the df.isNull.sum checks for any missing or null values in each column of the dataset, which helps identify columns that may require cleaning or imputation before analysis. And additionally, we also check duplicate entries using df.duplicated.sum to ensure data cleanliness, while also using df data types to highlight the different data types on each column. These steps provided are an essential foundation for pre-processing by revealing malformed and incomplete entries. Next, we move on to the data pre-processing, or more specifically, the clustering pre-processing. So here we mainly selected three RFM-like metrics, namely frequency, monetary, transactions, and aggregated them per customer ID. After removing these missing values and calculating the total spend per invoice, we applied the standard scalar to normalize these numerical features. This ensures that all the metrics contribute equally to the clustering algorithm without bias due to scale.
This code cleans and formats transaction data for market basket analysis. It removes canceled orders, incomplete rows, and non-product items. Then, it reshapes the data into a table of transactions versus products and converts it to 1 second and 0 seconds for use in algorithms like a priori. This code prepares for customer segmentation using k-means clustering. It first checks that the data columns are correct, then tests different numbers of clusters from 1 to 10. For each value of k, it runs the k-means algorithm on the scaled customer data and records the inertia, a measure of how tightly the data points are grouped. These values will later help create an elbow plot to find the best number of clusters for segmenting customers based on their spending behavior. In this part, the code generates an elbow plot to help decide the best number of customer segments for clustering. It plots the number of clusters on the x-axis and the model's inertia or within cluster error on the y-axis. As more clusters are added, the error drops. But after a certain point, the improvement slows down. That elbow point shows the optimal number of clusters to use for meaningful customer segmentation. The plot includes a title, access labels, and a grid to make it easier to interpret. This plot helps us decide how many customer segments we should create using clustering. It shows the inertia or clustering error for different numbers of clusters. As the number of clusters increases, the error drops, but after around k equals 4 or 5, the improvement slows down. That bend or elbow in the curve suggests that 4 or 5 clusters is likely the optimal number, giving us meaningful groupings without overcomplicating the model.
So after that, we initialized the k-means algorithm with four clusters, a number chosen based on prior analysis using the elbow method, which suggested this as the optimal value. The model was trained on scaled customer data using frequency, monetary, and transaction features. Each customer was assigned to one of the four clusters and was recorded in a new cluster column. To evaluate the clustering performance, we use two intrinsic metrics. The silhouette score measures how similar a point is to its own cluster compared to the others. A higher value, closer to 1, indicates well separated cohesive clusters. So since the silhouette score scored a 0.771, it suggests a strong clustering structure. While next is the other intrinsic metric we used was the Davis-Baldwin index, which evaluates intra-cluster compactness and inter-cluster separation, where low values are better. So since our score was 0.728, it indicates a low overlap and good distinctiveness between the clusters. Together, these results confirm that our clustering approach effectively segmented customers based on behavioral features.
This code reduces the customer data from 3 dimensions to 2 using PCA, making it easier to visualize clusters. Each customer is now plotted in a 2D space based on the main patterns in their behavior. The points are colored by cluster, so we can clearly see how customers are grouped based on similar purchase habits. The result is a simple and intuitive scatter plot showing customer segments at a glance. Now this is the visualization of the plot in 2 dimensions using PCA. Each dot represents a customer, and the colors represent different clusters based on their behavior, like how often and how much they spend. By reducing the data to two key components, we can clearly see how customers group together, helping businesses better understand and target different types of buyers. This code combines the original customer data with their assigned cluster labels and then summarizes the result. It groups customers by cluster and calculates the average frequency, spending, and number of transactions for each group. This helps us understand how each customer segment behaves. For example, which group shops the most often, spends the most, or buys the most items. This summary makes it easier to profile each segment and tailor marketing or service strategies accordingly.
So for part C, which is the market basket analysis using association rules, before we move on, I will be presenting a short research regarding the a priori algorithm. So the a priori algorithm identifies frequent item sets by generating candidate item combinations and pruning those that do not meet the minimum support threshold, making it effective but computationally intensive. In contrast to that, the ECLAT algorithm utilizes a vertical data layout and an intersection based approach, which is generally faster and more memory efficient for more dense datasets. So, when evaluating association rules, support measures how frequently and the item set appears in the dataset, indicating its overall relevance. Additionally, confidence also shows that the likelihood of the consequent occurring given the antecedent, while lift evaluates how much more likely the items are to occur than if they were independent. So from the association pre-processing earlier, Here, we start by displaying the basket dot head, which displays the first five rows of the basket data frame to inspect transaction item matrix. This is useful for confirming the one hot encoding structure where items are represented by binary values. And next we have the basket.datatypes.value underscore counts, which counts how many columns have each data type in the basket data frame. This helps verify if all the items were successfully converted to binary 1/10 for rule mining. Next, for the market basket analysis, we applied the a priori algorithm to our one hot encoded transaction data basket to identify frequent item sets with a minimum support threshold of 2%, meaning only product combinations that appear in at least 2% of all transactions were considered. To make the results interpretable, we use the use underscore call names equals true parameter so that the item names would appear in the output instead of numerical column indices. Next, after that, we generated the association rules from these item sets using lift as the evaluation metric and filtered the rules to include only those with a lift value of 1 or higher. A lift greater than 1 indicates a strong positive association between the antecedent and the consequent products, i.e., they are purchased together more frequently than by chance. We then sorted the resulting rules by descending lift values to prioritize the strongest co-purchasing patterns, which helps marketers and decision makers easily identify high impact product pairs for cross-selling and bundling opportunities. Finally, we displayed the top 10 association rules based on lift, including the key metrics antecedents, consequence, support, confidence, and lift, offering a clear view of product relationships in customer behavior. To prepare the association rules for visualization, we first converted the antecedent and consequent columns from frozen set objects to readable strings. This step was essential for making the rules more interpretable in both the tables and plots. Next, we created a scatter plot using the seaborn to visually represent the rules. In this plot, the x-axis represents support, showing how frequent the item sets appear in the dataset. The y-axis represents the confidence, reflecting how reliably the consequent follows the antecedent, and the left value is encoded in both the size and color of the dots, helping us quickly identify the strongest, most interesting associations. To enhance readability, we also configured the figure size, added axis labels, enabled a grid for alignment, and used a descriptive title. We also positioned the legend outside the plot area to avoid overlapping with the data and applied the tight underscore layout to prevent label clipping. This visualization allows stakeholders or anyone to intuitively understand the strength and quality of the association rules by observing how lift, support, and confidence interact in one visual format. So for the visualization, it is a scatter plot as stated earlier with the support on the x-axis and the confidence on the y-axis. The size and color of each bubble are represent the left value which also indicates the strength of the rule as stated earlier. So over here we notice that while most rules appear infrequently as shown by the low support, some have high confidence meaning they are quite reliable when they do occur. The most valuable rules are those with large, bright bubbles, which signify a high lift. These rules offer stronger insights and are worth investigating for potential actions or interventions.
Reinforcement learning, or RL, is a type of machine learning where an agent learns by interacting with its environment. It tries different actions, gets feedback in the form of rewards or penalties, and gradually learns what decisions lead to the best long-term outcomes. Think of it like training a dog. When it does the right trick, you give it a treat. Over time, it learns which actions earn rewards. In the retail world, RL can be used to optimize product recommendations. Imagine a virtual shopping assistant that sees what you are browsing. Based on your current behavior, your state, it suggests an item. That's the action. If you click or make purchase, that's a reward. Over time, the assistant learns which recommendations works best for different types of shoppers. Two popular RL algorithms are Q-learning, which learns the value of the best possible action at each step, even if the agent doesn't actually like it. SARSA, which is more cautious and learns based on the actual actions the agent takes. It's useful when the environment is uncertain or unpredictable. So, in a practical scenario, the RL agent could try different sequences of recommendations and learn. For example, that showing high rated items first works better for some users, while showing discounts first works better for others. The goal is to maximize engagement or purchases over time by continuously improving its strategy.